Okay, before the break, we were talking about a bunch of networking stuff, and took a moment there before restarting the recording to go actually look at the networking lab where the cables are and the switches and the routers and servers and everything for the School of IT classrooms here, which everybody has to take a networking class, so you'll be in there and probably notice that in the networking lab, all the wires and plugs and everything are exposed, so hands-on learning activities to do on your networking class. It's not going to be sitting around learning definitions, but for this class, it's sitting around learning definitions. So I want to take a step back, which actually I got out of order of what I was planning to do earlier. I want to take a step back to transmission control protocol. TCP. I just wanted to write it out to focus on the words again. Transmission control. So when we transmit stuff across our network, how is it controlled? The internet protocol just chooses the IP, just chooses the path we take. And then TCP actually controls what's going down that path. And I drew this picture. So we have some sort of file we want to send across the internet. We'll go and break it up into little pieces, small chunks. The term for that's going to be packet. And then with IP, each one of those packets finds its own way across the network and gets reassembled on the other side. So that's kind of what's going on, and each packet is padded with the OSI model. Did I write down what that stands for? I probably should have had in my notes what that acronym stands for. I know I've heard it a few times. I'll just Google it. What does, I'll share my screen and Google it. You all know this process. And while I'm doing this, I'll make it another tip. What does OSI stand for? So you all know the process, Googling, find it. Open Systems Interconnection. So we've had it with Open Systems Interconnection Model, obviously a mouthful. There's different ways, got quick search results there. But sometimes when you're searching for stuff, you might end up not getting very good results, right? I know this question came up with somebody's term paper or final paper and presentation for the class was informatics in the office, and the results all went to healthcare stuff, but wasn't really wanting to write about healthcare. So ways that we can filter the searches, there's other things. Nots and ands, and search engines will recognize those words, but a tip I like to throw in there is make a typo on purpose. This is what I found to be incredibly useful over the years, is if you're not quite sure what to look for, you're not getting good results, make a typo on purpose, or maybe a couple typos, and see what the search engine tries to correct it to figure out what keywords the search engine does know. I've just found that to be incredibly useful. I haven't mentioned it since I couldn't remember what the acronym stood for and had to Google something. I thought I'd throw that out there. Intentionally making a typo can be very productive in a search engine. Just so if you don't know where to go, you'll know how Google is. It will try to suggest what you're trying. It will try to figure out what you're trying to search for, and doing that on purpose can be very useful. Go back to the OSI model. Earlier, when we started talking about this, there was a bunch of stuff written there, like little notes about the overhead that comes with it, instructions on how to put it back together, what order are the packets in, and things like that. How is the information used? Because back to that technical definition of a network, we're transmitting information, not data. So we need to say how all of that stuff, and that's where the OSI model comes in. This is all the extra stuff that's included there. And there's 7 layers. I'll start down at the bottom. Now at the bottom, the lowest level is the physical layer. And the physical layer is the bits making up the data. That's supposed to look like an arrow. Bits making up our data that we actually want to transmit. The raw data itself, that's where that fits in. Then we have a data link layer. Which represents the format and transit. So each one of these packets, that's a long string of ones and zeros, right? So is there anything, little information about that? The parity bit we talked about, throw that in there, just an extra bit to make sure we have the appropriate parity. If the other computer is expecting an even number of bits to come through, that we have an even number of ones showing up on the other side, or an odd number, vice versa. And a few other things, and there's some other things in there, but you'll see those in the more advanced classes. Basically, just remember the data link is the format that it takes, or that name actually fits in here. So the network layer is next. And the network layer has the physical path taken. So those three together, hopefully sound familiar from earlier today. The physical path taken is going to be the IP protocol, right? So we'll get off that, continually checking and keeping track of all the machines we've popped through along the way, so that we don't get stuck in a like loop between this same 2 machines, because neither one can connect to anything else. And right in between them, data links, so the bits making up the data are connected to that route taken. How does it break up into packs? So the bits, and then little information like, well, they're traveling 1024 bit packs, 1024 bits in each one of the packs. Actually, it'd be less than that. So each packet is maybe 1,000 bits, and then we have a parity bit, and then we have a couple other things that had for how our data was broken down, basically. Because it doesn't break it at logical points. It just grabs those bits, and if we say send, like I just used, I'll just say 1024 bits in a packet, it just starts at the beginning of that binary code and grabs the first 1024 bits. Doesn't matter where it ends or not, whether it's a logical place to break it up or not. Transport layer, and a lot of that information I just mentioned is spelled out more explicitly. And so this is the 1024 bits. This is each of our packets. So the bits themselves in the packets, and then this is the protocol data. As in TCP protocol. So this is packet number 1, this is number 2, this is number 3, this is number 4. Referring to a picture, obviously it would look a little bit different, but packet number 1 goes in the top left, packet number 4 goes in the bottom right, and those sort of information. That sort of information. Each packet is 1024 bits. packet size, number, stuff like that goes in there. Then we have the session. The session layer is the two machines that are connected. Two machines that are connected. So the start and end. Where did this communication start at, and where did it end? So for the case of people on the Zoom call, the audio that starts at this speaker microphone combination on the wall travels over to this computer, goes to all those other networks, and eventually reaches either Luddy or Amaj's computer somewhere else in the world. The start and end points of the connection. That way it's separate from the list of all the machines we've traveled through, and there's no confusion. We don't accidentally confuse one of these machines with one of the endpoints. We're going to fully separate them. The presentation layer which has sequence, encryption, and the actual format. Sequence, encryption, actual format versus the format in transit. So might not necessarily go through in the same order that it belongs in. When we talk about image data, I like to throw that in somewhere. So usually around week 7 or 8 is one of the things we have time for, and it's not covered anywhere. Like if we're going to use an image, we just grab the image we want to load it in, JPEG, a PNG. But those internal differences. Why does a ping hold clarity until we stretch it a lot, keep clarity if we shrink it down? Bitmaps get blurry if we stretch them up, but they stay clear if we stretch them down. JPEGs get blurry if we change it at all, if we go up or down. Those differences. The different types of formats, talking about them internally. So when we use them, we're just going to grab the picture we want and use it. But I like to cover it because it's not talked about anywhere, and it only takes about half an hour to go through all of them. So usually we see that in week 8 in this class, those subtle internal differences. But when we get to pings, the bits in order versus our layers. And that's what we'll call them in pings. So jumping ahead a little bit there, but the actual format the data goes in. And then at the top is application layer, which is the software to use. So what software actually processes that actual format of the data after we put it back together? So how is it put back together? So these are the steps or instructions on how we break it down, send it across the internet, and then put it back together on the other side. You will see that quite extensively in your network infrastructure class. For now, just be aware of the layers. Kind of try to remember those names: physical, data link, network, transport, session, presentation, application. Or really this, I put it here because this is a preview, because when you take your network infrastructure class, you're gonna have to have that memorized. So we preview it now. And that way it hopefully be a little bit easier to memorize when you actually have to memorize it a year, 6 months, a year, 2 years from now. But hopefully just sort of preview on a lot of stuff and vocabulary terms, and definitely words you'll need at some point. It's okay if everybody says no. Yeah, I had to take what's normally 2 lectures and put them into 1 this week because of the holiday. So I'm jumping around through the notes and kind of going in different orders. There's one more thing in the notes I want to include because it's something you will hear about over and over and over again. That's going to be ports. So how we connect for different purposes. It's a software-based 16-bit number. So basically, the client and the server have the same piece of software running on them that sets up a number, and they just agree on that they're going to connect with this extra number across this number to make sure it's the connection they want. Because at any given time, one client might be connected to several servers, and one server is definitely going to be listening to lots of clients at the same time. And also adds restrictions and security and stuff to make sure that we're connecting in the correct way. For example, if 2 machines connect on port 22, that's for SSH connections, secure shell. So one of the machines is tying into the other one so that it can use terminal functionality, so that it can run terminal commands on the other machine. And obviously we want to do that secure, so there's an extra S beside the shell part. Port number 53 is for domain name services. We're talking about IP addresses, which are just sets of numbers, and I'll probably just starting to pull up some on the computer to talk about those, which is how the machines know about each other, but not very useful for humans. We would never keep track of it, how we access different things. Yeah, we'll see that in the example. It's that one that's definitely in the lab. So we have domain name services where we put a human readable name on it. So instead of just making up one, so instead of machine 123.123.45.39, we put something on there like mysite.com that a human is going to keep track of and remember easier. And if we need to do any of that stuff, we connect the 2 machines, just agree on this connection number. It's not like a physical port. It's not a different wire. It's a software connection. 80 is HTTP, Hypertext Transfer Protocol. So that was the big step forward between the original idea and ARPANET, like we talked about. Around 1989, somebody came up with a great idea. Instead of transmitting you the data, why don't I just send you the address of where that data is at? You can go get it if you want. So links. Just instead of sending the data, I'll just tell you where to get that data. Because that's usually a lot smaller. And y'all have used links before. Hypertext links. Hypertext linking is the name for that. So Hypertext Transfer Protocol, which in the 80s, security wasn't a big deal. So on port 443, at some point later, we got a secure version of that, HTTPS. And and that idea is what really made the internet take off, like for what it is today, World Wide Web. A couple of years before the government started researchers, so only people at universities and colleges could transfer across the internet along with the government, because they paid for the whole thing. And then in the latter part of what we would still call the middle 1980s, the government allowed commercial traffic. But then in the late 1980s, somebody came up with that idea, right? As soon as the data, how about I just send you the address of where that data is at? And You can go get it if you want it, or ignore it if you don't. And then we don't bog down the whole network. That's what started the World Wide Web. Why a particular internet got the different article, the internet, instead of just an internet. 3306 is MySQL. So if we wanted to connect to a MySQL database, we just put it on port 3306. And the big thing is it's a software number that both machines agree on. So sort of a connection thing so that we know how to look for it. Let me share my screen real quick. And I think I have Jamp on here. Hopefully it's not broken right now. So if I start a couple things. This is just a little virtual server. We'll talk about virtualization. Oh, I was talking about that starting. There it goes. So I have 2 web servers and a database server that I hit the start button on there. And when we can tell what's being transmitted back and forth between the client and server because of the agreement on the port number. If it comes down port 80 or 443, it's going to be HTTP traffic. Port 3306 is stuck with the MySQL database, and anything on these two, 8005 or 8080, is going to a Tomcat server, which is website stuff, but it's controlled by Java. Has Java running, a Java application running to control all of it, which we could just then go over here and so there's a special term to refer to our local machine if we want to say local host. Well, I started that one, so colon 8080. I was doing some stuff the other day, and so the browser wants to go back there. So local host refers to our own machine. Computers know about each other by name, so it's actually 127.0.0.1 is the machine you are currently working on. That's one you might want to memorize if you head into IT. 127.0.0.1 is the machine you're on, which, going back to that DNS thing, humans do better with words. So we can also access that by the word localhost as one word. You probably also encountered 192.168.0 and 192.168.0.1. Those are the I don't know why I was going to put a picture. Those are your closest router. So the closest router to you is going to be 192.168.0.1, unless you change that, unless you went in and actually told it to be a different address. That's what your client machine knows the closest router is. Common ones, but if we go to that address, and then notice colon 8080, colon means port. So that machine connect on port 8080. Oh, whoops. I typed a semicolon instead of a colon. 127.0.0.1 colon 8080. And that opens up a Tomcat server, which is a web server that runs Java on the server side. I just go to 127.0.0.1 and get rid of the port number. It opens up this default page, but it jumps to an Apache server. And if I come in here and explicitly type port 80, it goes to the same thing. So 80, it's a web browser, so our web ports are implied there. I don't think 443 will work. Yeah, if I go to 443, it says you're speaking plain text to an SSL enabled port. You're not secure. Have to be secure on this. So the machines agree what port it is, and that little virtual server running on my computer is like, nope, you're not secure. I'm not going to connect. I'm not going to communicate with you. You didn't fit the criteria to communicate on that port number. That's something you'll see. And when you need the ports, it just goes in your address bar. This IP address. What we're getting ready to talk about, but I think everybody's probably encountered IP address at least once in modern America. The IP address is address. You just type it right in the address bar. And then domain name services are an extra thing on top of it, so we can use human readable words. So like your own machine is called 127.0.0.1. It's always going to be the name of your local machine. Sometimes 8.8.8. Is that going to loop back? Nope. Mine's not set up for that. That's another common one you'll see for also called a loop back. But we're humans, so we can also just use the word localhost without a port number on it and get back to the same page instead of typing in the numbers like the computer could see. So I guess, yeah, be aware of a port number and how to enter a port number. So after you type the address, the domain you want to go to, put a colon, and then the port number, and then a slash in the rest of the domain. So it only goes to the top level domain. So I guess in general, after the .com, there are a bunch of others, right? .edu, .gov. That's the top level domain. That's the main server holding the rest of the pages you want to see on that site. So after that top level domain, colon, port number, and then slashes for whatever file you want from that server is where it goes in. So IP addresses. Machines need a way to talk to each other. This machine, well, it organizes other machines. So we have these collections of 4 numbers. So 10.8.20.100. 4 different sections, and all of those will go from 0 to 255. It's Internet Protocol version 4. Again, back to the 14 to 19 lines of code. Version 4 and version 6, the same software runs on both machines. We saw coding last week, software development. It has an if-else structure. Versions 1, 2, 3, and 5. There's client software and server software, so they're running different things. And on 4 and 6, there's an if-else block or some sort of selection put in there, so that whenever something comes across the network, the same software works for clients and servers. That's why those 2 really took off. But it had 4 8-bit numbers, so 256 available things, and 0 is one of them. So from 0 to 255, and we put together 4 of those. Seemed like a lot when they created that back in the 1960s, but we have a lot of machines that we want to connect our computer to, right? All our cars and phones, and they did not know all that stuff was going to need IP addresses as well. So it kind of ran out. So we also have hexadecimal, which is a long string IP version 6, which has a long string of hexadecimal digits, way more bits, so lots and lots and lots of bits. It's not broken up, but we will see colons in there, which are the colons are for human readability. That way we're looking at it at four hex chunks, 4 hex digits at a time, because there's a whole lot of them in that address. We realized how many computers there was going to be, so we need a really, really big number. So even when we read it 4 bits at a time in hexadecimal, there's a lot of them. And if there's 2 colons, it's abbreviated. So everything between there is either all zeros or the same as what came before. So FE80, a whole bunch of FE80s, and then the rest of these, and then you would just take note of how many are missing from a full IP version 6 address and those columns. But just a lot of digits, and then that one is only broken up for human readability. Let me turn on the WSL. Something I'll pull up. Windows machines now have Linux, and when we Linux subsystems, we're going to talk about this in module 7 when we look at virtualization. And when we turn them on, it's actually a subnetwork. So if I run that same command again, ipconfig, it added something. So notice now says there's an Ethernet plug, but you all can, at least to those in the classroom, can see there's not any Ethernet connected to my laptop right now. So it recognizes that way, and I got another address here. So this is the router over there, over in the other room, like we were looking at the end of the break before the recording started. Over in the networking labs, one of those routers has this IP address. So I'm connected to that one. But now I got this other IP address, 172.224.1. And notice right below it, there's this thing, subnet mask. And the first two sections have the highest value that we can put in an 8-bit number. All at once, it's 255. 11111111. It's 255. So those are just all ones. And then we have something different down here, 240 and a 0. So we put those together as an AND situation, and we can create more numbers. So all of these zeros and ones put in columns and going downward, and all of these zeros and ones give us more space to work with. Because if we do and 1, it doesn't change anything. So our first two ones stay 172.28. But in these, when we do and something else, it changes things around. You'll see that. You'll see subnet in your networking class. Something we usually want to do, but it's a mask. So we kind of put it together with ands and ors for those really ands. So these two don't change. And if I jump over to the Ubuntu machine and ask for the IP address, I'm going to grab and filter this, it would return a lot. Notice this machine, it's a virtual thing, but it's 172.28.230.206. So a different number, but those first two are the same. So those are like the network. That's for the little network, those first two. And the subnet mask didn't change those, but it went ahead and changed the other two and added the /20 to show which variety of those last two sections it's in. Same thing over here. IP address, and this is just a filter. I'm going to look for something called INET because I know that's the number I want. If I just ran this in, if I just ran that instruction, get a whole big mess of things. So this other part is just filtering it down with what's called regular expressions pattern matching. But here again, we have 172.28 and then a different couple numbers there. They're the same. I'm not sure why those two are showing the same number. Okay. Okay. Those should not be showing the same number. That might be something that I might have broke something in my WSL. Those should be two distinct machines on there, but you can see that it connects on that network, and the machines know about each other, whether real machines or virtual machines that way. Or anything. So, and let's look up. This is one that's in your lab. For homework is ivylearn.avtech.edu. .edu, you'll look this up, and here's the actual. So anytime we type that in, it calls these addresses. Should be 3 of them. So it tries to connect to that address. If it doesn't respond, it goes to the second one. If it doesn't respond, it'll go to the third one. So there's multiple addresses because obviously a school's learning management system will sometimes get busy, and lots of people will try to access it at the same time. So we need fallbacks. You can see here it's on an AWS server. We grab that and figure out where it's at in the world. We grab this. Location of this. Maybe I don't want that. Location by IP address. Okay, IP address lookup. IP location.net is a good one I've used a few times. So if we go in here and paste that address, oops, and look it up. We're gonna find it. Okay, yeah, so it's say that, well, it belongs to Amazon Technologies somewhere on AWS in Virginia, and here's our latitude, longitude. So if we look these up, let this number come along. Should be able to find that right on the map. There it is. And there on. There's that one. Whatever that was. We can look it up. If you look up that particular one, you'll see a big parking lot. It's AWS's main server farm, and they built a really, really nice playground on top of it. So the location gives the parking lot where the staircase leads down to it. You can just look up the latitude and longitude, and you can see that from that IP address, we can find where it's actually at from lots of different sites. There's some stuff like that in your homework this week. What else is there? So yeah, NS lookup. If we know the domain name, we can go look. We can go find that. My.ivtech. I'll go with our other one and see this one, and you'll notice it's not an AWS server. This one actually belongs to IVTech, not to AWS. Or we're not using an AWS server for this. And you also notice it doesn't have a bunch of fallback addresses. Because even though that has the email and all the work stuff, don't expect that to get, it's not expected that that's going to get cluttered like the learning management system does at, say, 11:50 on a Sunday night, 10 minutes before everybody's homework's due. IP config is definitely on the thing, so that'll give you your information about your computer. There's step-by-step lab instructions. NetStat. So this will tell all of the computers, so the rest of the network. Up until we hit the router and leave to go to another network, there's a bunch of other machines here. So this will list all of those out, and then we can find further information about them. Which also how many machines are in there. So it's gonna, there's a whole bunch on the same side of the router as I am here. So Control C will cancel that list. You want to see if something's up. I think this one has become pretty common, like a ping. We can just send a bit over there to see if the other machine receives it. I relearn you, which is definitely going to respond. Tells us how long it was and all that. IDU. And if we grab one of those IP addresses, you can also ping the IP address directly, ping that, and should get approximately the same responses. If your computer's set to not stop there, sometimes Windows machines fit by default to just keep pinging a machine. Push Control C, that's canceling any terminal. What else? Trace route. Nope, that's not it. Trace route. I rarely use this command for anything. Trace route. In Windows, you all know the routine, right? Go look it up. No, I don't mean. I put the traces spelled out and routes abbreviated. Linux machines are the opposite. Trace is abbreviated and route is spelled out. Trace route. I'll go back to our LMS. I learned .ivtech.edu, and this checks the network layer, the physical path taken. What machines are we going through in order to get there? So 10.8.61, we saw that earlier, that's the router. 168.91.1.3, wherever the router connects to after that, it's probably the same thing. And we're on a college campus, so like most colleges, all the Ivy Techs across the state of Indiana have fiber optic cables running to Fort Wayne, where we tie in directly to an internet backbone, so we don't have to go through Spectrum servers and all that. So when you do this from home, you'll probably see Spectrum servers on there. Some stuff that is specifically for education networks. Colleges, the researchers the military hired in the late 1960s had their own motivation for creating the network, so it's been built in from the beginning. They included the stuff they wanted to do as well. And I think, yeah, now it's just things have started timing out. So we're probably about where it's going to be. And it's trying to get to another server and things keep timing out. So that'll happen sometimes. It tries different servers until it gets back on the route. I think it's actually 150.222. I think it's actually already reached the server farm in Virginia. And it's just randomly bouncing around the servers there at AWS's main server farm. So it might do that for a minute. That's on the lab. Control C to cancel that again. And that tells this information, the physical path taken, which servers did we go through to get in order to get there. I think in the lab, I have you run that twice and compare them. Some people, sometimes you'll see the same route taken, other times it's a completely different route, different amounts of time on each server. So pay attention to the details on that. If you get the same route twice in a row, try it later and see if you get a different one an hour later or something. Like always with the lab, there's step-by-step instructions on that. If you have any trouble, let me know. I think that was everything I wanted to talk about with networks. Let me quickly double check my notes because again, usually there's 2 days to go 2 days in the network module instead of one. So the picture of stuff, the ARPANET leading up to IP protocol, the transmission control protocol, and other protocols exist, but TCP is quick and easy. So once machines can handle the overhead, we haven't really looked back. Break things up in packets, and each packet finds its own route through the network and includes the instructions on how to reassemble it on the other side. Those top 2 layers in the OSI model. Port numbers are just sort of a software agreement on how they connect. Yeah, I think that was a lot of the key points, a lot of the key terminology, like so many things in this class. In preview mode, this class is a lot about making sure that you're in a good position to start your IT studies. We're previewing everything, and everybody has to take at least one networking class. So you'll see this in detail in the other lab where you get your hand actually be doing stuff instead of just seeing the definitions written on the board. Does anybody have any questions about this stuff though? Okay, so there's another step-by-step lab where you will open whatever your local terminal application you use and work with some of the network commands there to control the network. If you have any questions, let me know. Otherwise, I will see you all next week. Everybody have a good weekend.